Swayam Prabha. Digital India. Educated India.
Okay. So, we were solving this problem of making the stiffest beam for given amount of material. We got our design equation, adjoint equation and complementarity condition and the equilibrium equation, and we said that when we looked at the adjoint equation. So, let us look at the equation. When we took the variation Lagrange respect to W, we got an equation that looks like this, okay. And then we said that if you simplify you will get to this, which leads us to the conclusion that lambda equal to minus W. That leads to a very interesting optimality criterion, that strain is uniform and hence stress is uniform and hence strain energy density is uniform. The simplification which I have done here, which I hope you did after the previous half of the lecture. So, this is what we need to simplify, which if we do step by step, you do not have to expand everything ahead of time because things get cancelled. If you see, the first step implies, the first line implies this line where I am leaving this as it is and I am also leaving this as it is and expanded only this last one, okay. Then this 2 and this get cancelled. And then next time I am still not expanding this, but I expanded this thing and this particular one also I expanded. So, everything now except Q has a double derivative. Again I can see this and this. So, this and this get cancelled and this and this get cancelled, leaving out only this term, which is this. If we compare that with the equilibrium equation that we had, which was E alpha A W double prime minus Q equal to 0. That was the equilibrium equation from above, which we had also derived in the last lecture, equilibrium equation. If we compare these two, we immediately conclude that lambda equal to minus W, which when you submit the design equation gave us the condition that lambda is equal to E alpha W double prime square. So, the optimality condition here, the optimality condition here is lambda equal to E alpha W double prime square, right. Again you see how it came about. We had this as the design equation and then we substitute for lambda double prime minus W double prime, that gave us this, okay. Again let us remind ourselves that alpha is d square by 12, because in this problem we have assumed that d is given, it is part of data. So, this is the condition we got by writing or manipulating the design equation, but there is no design variable here A. This is exactly what we had for the bar as well, but it does help us compute area of cross section because we know the equilibrium equation, which is E alpha A W double prime minus Q equal to 0. Now, from here we can substitute for W double prime, okay. So, if we do that, I get E alpha A into square root of lambda by E alpha, right. That is W double prime we substituted and then double prime minus Q equal to 0. So, even though there is no A explicitly over here in the optimality condition, it does come about when you put that into the equilibrium equation. So, once we have here, we know that these are all constants. In fact, I can rewrite this as square root of E alpha lambda, all are constant except that we do not know lambda, times A double prime will apply only to A because others are constants, right. So, that is equal to Q, which is given to us. So, if I want to get area of cross section, I just need to integrate twice, that E alpha lambda that I have, okay, times I will have integral of Q of x. First time, let us write step by step, A prime, I will get Q dx. Q is a function given to us, we can integrate it, and then there will be a constant, okay. And then one more time if I do, I will get 1 over square root of E alpha lambda, and then we will have this one more integral Q dx plus C1x, and then we will have C2. Okay. Now, we have conditions boundary conditions which we are not writing, but I encourage you to do this because it is an application of calculus of variations. We had written all the general boundary conditions, you write them, which will enable you to solve for this constant C1 and C2. If you know Q, you can integrate twice and then C1 C2 the boundary conditions, then you get A of x, the problem is solved, okay, analytically, right. We do not have to resort to numerical things here, okay. If Q is a load that is not integrable, then you need to do numerical integration only for Q twice and then you get the answer, okay. This can be done. What happens if we go for the moment of inertia, second moment of area I, not inertia. This I, we had written it as A raised to beta, and we had two possibilities. D is assumed, that is what we did until now to solve this, and the other we had said is B is assumed, right. So, this gave us alpha equal to D square by 12 and beta equal to 1, which was easy. And now, if B is assumed, alpha was 1 over 12 B square and B equal to 3. Okay. Imagine that we had to expand this term, that is we had E alpha A, we had that earlier, E alpha A W double prime, which we expanded it, right. We got something before. Now, that becomes E alpha A cube W double prime. So, expanding this will be much easier than expanding this and doing the calculation. Now, you see A cube is there, beta equal to 3, it will become a lot more terms, but that can be done. If you go to Mathematica, you can do it by hand. You can do it by hand as well. If you use Mathematica or a symbolic manipulation software, it will do all the expansions for you, and then you can write down Euler-Lagrange equations, just simply taking partial derivatives as we have seen for the design equation and the joint equation. So, what we have here, you can do all of this using Mathematica or Maple and or by hand, which is doable. Finally, what you would get when you do all this, that is something that we should remember. We will be getting the design equation, because of taking Lagrangian variance with respect to design variable equal to 0. Okay. And this design equation will have particular form. There will be some expression times lambda times some expression equal to 0, that is form of the design equation. We had already said that this particular thing will be gradient, it will be an expression meaning at every point x gradient of the objective function. gradient of the objective function. Okay. That means that if I take the objective function and take its derivative with respect to a, in the sense of calculus of variations, whatever you get will be the expression for every value of x. If you evaluate, that will give you precisely the gradient, and this particular thing is going to be gradient of the constraint. When I say constraint, not the governing equation, that is just a state variable controlling equation, that is really not a constraint. The real constraint here is the volume constraint, that is what, because the corresponding lambda is there for that constraint, that will become the gradient of that. If we go back and look at the case when D was assumed, our design equation, if I go all the way up here, our design equation look like this: lambda minus E alpha W double prime square equal to 0. If I now plug that in here for that problem, so this is E alpha W double prime square with a minus sign, and this is 1, right. That means that this is the gradient of the objective function. Objective function here is the mean compliance integral of QW. If that integral, if you take derivative at a particular a of x, okay, a of x is a function, let us say at particular value of x, if you take a of x at that cross section, if you change only there, how much, at what rate does the objective function change is given by this expression. So, let me reiterate that, saying that in this problem, as it will happen in any problem, if you look at what is in the parenthesis, E alpha W double prime square is the derivative of a of x, a particular a of x, any value of x, of the objective function, which is the integral 0 to L q w dx. And this has to be understood really well, because you have an expression to say what happens. I have a beam, okay, let us draw a beam profile, let us say that is optimum, let us say this is optimum, somebody has told you it is an optimum. Now, or even otherwise some profile is given, let us say at some value of x, let us say this is our x, at some value of x, if I change the cross section a little bit, okay, let me use some color, some material I want to add, then obviously under the loading Q, if I compute W by solving equilibrium equation, I will have a different mean compliance, right, compared to the one without this additional blue, right. So, what is, at what rate that is changed is given by this, okay. And likewise in this case gradient is 1, because the volume constraint we have integral a dx with respect to a, if you take derivative you get 1, and that is what we got, okay. Design equation will always have this form, and adjoint equation will always have the form similar to the equilibrium equation. If numerically, if you have a finite element routine to solve the equilibrium equation for W, you can also solve lambda, because what will be different is just the loading. In this particular case, loading turned out to be minus q. Let us look at that equation again. We got, if this is the equilibrium equation, we got this as the adjoint equation for solving the adjoint variable lambda. Here if you see, the loading, real loading is minus q, here it turned out to be plus q, meaning that loading is minus q, okay. So, this is a consequence of the objective function which we have q integral wq qw dx. So, what we have there is essentially the adjoint load, which is simply gradient of the objective function with respect to the state variable with a minus sign in this case, okay. So, if you follow this procedure, you get an adjoint equation that looks exactly like the equilibrium equation. If you have finite element routine to solve for W, you can also solve for lambda, which is very easy, straightforward. Once you know q and lambda, you have the expression for the derivative objective function in the design equation. If it can be analytically solved like we did in the previous example of assuming d to be constant or given, we had analytical solution. But now if you have other situations, let us say other objective functions and more constraints, you may not be able to solve it analytically. So, let us say that we have, in addition to volume constraint, we have some constraint on stress or buckling or frequency or whatever. Then design equation which is obtained by taking the variation of the Lagrangian with respect to the design variable, we get something, and that something again is the gradient of the objective function plus lambda into gradient of the corresponding constraint, here the volume constraint. Let us say I have another constraint whose let us take it as a functional type constraint. Let us say the gram multiplier corresponding to this gamma, right, but that also will have something here, and that will be equal to 0, and this will be the gradient of that constraint. Okay. So, you have expressions for gradients coming out of this analysis. So, if you do not want to solve analytically or you cannot do analytically for complicated problems, this procedure, this analytical procedure is still applicable because you get expressions for the gradients. Once you have that, you can go and use any of the nonlinear or what we call mathematical programming techniques, okay, which are plenty these days, readily implemented in, let us say, MATLAB. MATLAB toolbox has fmin-con constraint minimization routine, which solves using sequential quadratic programming and trust region methods, and there are many more. And any of those mathematical programming techniques or constraint minimization algorithms can be used to solve, because now you are able to supply the analytical gradients. That is the beauty of this analytical procedure. You have the gradients. When you have gradients, algorithms will be happy because they do not have to compute them using finite difference, which will be time consuming, because you have to perturb each variable at a time and do repeated finite element analysis. If you have, let us say, 100 design variables, you have to perturb 100 times that delta A1, delta A2, delta A3 and so forth. That will be time consuming, whereas now we have analytical gradients. Okay. That is, if you want to use these package programs or blind or black box programs, where you just supply your problem and the gradients, they will give you the solution. But if you want to write your own programs, the design equation is still useful. Let us say I have a design equation such as this. Let me just, for the sake of writing, I will just say this is m plus lambda times n. Okay. Let there be another constraint, but we will set that aside. Let us say I get something like this, m and n will be some expressions, okay, which we can compute as soon as we solve the governing equation. That governing equation we can solve whenever we have a. So, we assume, let us say, iteration a0 of x. We assume that in any optimization problem we need to have an initial guess. You have to start somewhere, initial guess. You take that so that it satisfies the volume constraint. Okay. Make sure that it satisfies volume constraint. That is easy because you make it uniform. Okay. Then you will make it, let us say we have a beam of length L, you are given some V star volume, you make cross section everywhere V star by L. If you integrate, you will get V star, right. So, if you do that, make A0 equal to constant, I would say, in fact V star, if you have V star by L constant, because both are given, V star is given, L is given. So, it satisfies volume constraint, it satisfies the volume constraint. Okay. Now, taking this equation, we can use that optimality criteria method, okay, optimality we are using the optimality criterion here, that is why it is called optimality criteria method. We use plural even though we have one criterion, but remember that we had adjoint equation, other criteria, they are all combined into this. What we do is that m plus lambda n, which should be 0, we add it to get a1. So, a1 of function, the first iteration. So, this refers to the iteration number, this refers to iteration number. Okay. So, this we say we add it to the first iteration function we had plus this m plus lambda times n, which is all calculated at 0th iteration. Okay. M will have some expression. In the case of the D assumed, we got this as minus E alpha W double prime square and n was 1. So, we will always be able to compute that once you solve the governing equation where state variable is computed and hence its derivatives can be computed. There is this lambda that we do not know, but for that we have the equilibrium the volume constraint, which is active by the way, because we got lambda equal to E I W double prime square, which is the design equation. If lambda equal to 0, W double prime equal to 0, W double prime equal to 0, if put in the equilibrium equation, then that will lead to a conflict that something 0 plus q equal to 0 or minus q equal to 0, right. That is why we said lambda cannot be 0, that means constraint is active. Constraint is active, less than equal to sign goes away, then we have 0 to L A dx is equal to V star now, not less than or equal to anymore, equal to, because lambda is not 0, lambda is 0, W double prime is 0, W double prime is 0, equilibrium equation will have a conflict. Okay. So, once we have it, we substitute the new area A1, that is here I put A1, that means that I have to do 0 to L A0 plus m plus lambda n, all of this integrated with respect to dx should be equal to V star. If you look at that, what are the things that are known? This we know, this we know, this we know. What is not known, and also V star is known. What is not known is lambda. It is only one equation, right. We can actually calculate that. We can calculate this now by taking all the things that we have to the other side. So, V star, okay, divided by first I think not divided by really, okay, let us just do this. I will write the lambda part of it, lambda into 0 to L n dx. N is equal to 1 here, but let us do it right. In general you may have n something else. So, n dx equal to V star minus 0 to L A0 plus m dx. Okay, I have taken this to the other side and I have this now. So, what I get is lambda is V star minus integral 0 to L A0 plus m dx divided by 0 to L n dx. Okay. So, basically you have n equal to 1, it will just become L, but in general you can get lambda. That is also analytical because our constraint here is linear in area of cross section. If it is non-linear, we have to do that also numerically, okay. But in whatever case, a single variable lambda is our variable now, we can find that using an equation. Once you have that lambda, you can update A1. Once you get A1, you get A2 in a similar way, that is wherever 1 is, we have to replace that with 2, this becomes 1, this becomes 1. Then you have to get lambda for that iteration using the same way, and you keep on repeating it until this becomes 0, meaning that A k plus 1 is very close to A k or towards satisfaction, very close. You have to define when do you want to stop, how accurate do you want the optimal structure to be, optimal profile to be. You stop, meaning that then this will be 0 at convergence. That is exactly what was our condition. that m plus lambda n is equal to 0. That is what we do. Okay. That is how the optimality criteria method works in numerical sense, whenever you cannot solve the problem analytically. We had done this for the bar, we will do this for the beam in the next lecture. So, you can see that. Before that, before you go to the numerical implementation in the next lecture, we should also consider the fact that you might have upper and lower bounds on area of cross section. If you do this, sometimes area of cross section may turn out to be negative or maybe 0, which you do not want to tolerate, or become so large in some places that you may not want it. So, I can put in additional constraint that area of cross section at any value of x has a lower bound and an upper bound, right. In fact, in this there are two constraints. One is, since we always write everything in the form of less than or equal to AL minus A less than or equal to 0, A minus AU is less than or equal to 0. For these are local constraints, right, because these are function type constraints, local constraints. These are local or function type constraints because they are everywhere for all values of x. So, I will use lowercase letter mu, we can call it mu L of x and then mu u of x, two additional multipliers. Okay. So, accordingly when you write down the design equation, this will have minus mu L will come here, plus mu u will come in the design equation. So, for this problem if you were to write, we had this capital lambda minus E alpha w double prime square, and then we will get minus mu L plus mu u equal to 0, right. Now, we do not know this mu L and mu u. When do they come? Because we also have complementarity conditions that come from these constraints, right. That is, we will have mu L times A L minus A equal to 0. Since they are less than or equal to, we want mu L to be greater than or equal to 0, and then mu u times A minus A u equal to 0, and hence we get mu u is greater than or equal to 0. That is, these two functions that we have here can only be non-negative, they cannot be negative. That is what these things illustrate. So, we have to find them. Actually, we do not have to find them, because whenever it reaches that, when you are updating your area profile in this manner, when you are updating in this manner, as you find the uppercase lambda, you check after you do this whether area of cross section anywhere is going to disobey these bounds. When they disobey, you push them to that. If something is exceeding AU, you bring it down to AU and fix it at that. When something is going below AL, you just make it stay at AL. In that case, what happens is that area of cross section is already known, because if you make anywhere AX of kth iteration numerically you are doing, if it is less than AL, less than or equal to, we can say, then you simply say A equal to AL for that point, for that value of x. Okay. Similarly, if A of x kth iteration is greater than AU, you basically make that A at that point AU. So, if you have the domain, okay, 0 to L for different values of x, there could be some domain where it is reaching the lower bound, let us use A for the lower bound. There could be some where that could be reaching upper bound. Okay. Rest of the blue is in between, which is controlled by your expression according to the design equation. So, when you are trying to find the lambda using this equation, you do not have to worry, because that 0 to L is now split into 3 different things. We will have the first one no constraint, second one lower bound constraint, third region upper bound constraint. You accordingly split your 0 to L A dx into 3 regions: lower bound region, upper bound region, and then unconstrained region, okay, and you do similarly this calculation, you will always be able to get lambda and you proceed. Okay. So, we will solve a problem where we will have lower and upper bounds on the area of cross section and numerically illustrate to you in MATLAB with a code that you yourself can also run after we go through a few examples, both for a bar we had done earlier, now we will do for the beam, so that we understand this clearly in the next lecture. Thank you.